welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Okay, we're starting off. Hello, and thank you for coming here and listening to this. You know, when I first had my first computer, it had a 4 megahertz clock with 640K of RAM and a 10 megabyte hard disk, and the cost was several $1,000s. Today, my phone has 1,000 times more capabilities at 1/10 the cost. How do we reconcile that with our modern EW systems in these tight financial times where they want faster, better, and cheaper, and we're demanding more from what we're doing? In this talk, we're going to talk about some of the challenges and the new methodology to model that system and get it moving quicker and more efficiently at less cost. I'm going to be talking about that, and then Din-Ching will take over and talk about some of the key models and simulations in electronic warfare and radar, followed by an integration of both design and test to help reduce costs and improve flow. And then I'll finish up talking about some virtual situations where we can model what's going on with real aircraft moving in real tactical situations. Okay, so first of all, we have this system, and we want to look at how do I get started with a system? How do I develop a system? And how do I verify that that system works and meets the performance specs at all stages of development, not just when we put it all together at the end and find out that it doesn't work. What I call continuous validation or verification. What do we do if I have multiple radars and also jammers and plus interference all applying to our system at the same time? And how can I reduce the cost of flight testing, which is one of the big costs associated with testing of radar systems? It costs like $100,000 an hour for this. And also phased array systems can cost significantly more to test because you have thousands of channels instead of just one channel. And then what do I do if I'm doing repetitive tasks so I don't have to keep redoing it over and over again? How can I simplify those designs? So what we're proposing is a new platform using Agilent System View that allows us to simulate at all stages of the development process and to implement not only the System View IP, but also your own existing IP. Many of you have many years of experience and lots of algorithms and work you've done, whether it be in MATLAB or C code or even Fortran, and you want to integrate that IP into the overall design. We can also implement, for instance, custom models using HDL. If you want to put an FPGA and integrate that in, we can do that. So anyways, this allows us to control also the program, for instance, from C# or MATLAB or LabVIEW even, and validate performance of the whole system in a tactical situation using SDK from AGI. So here's an example of a simple system where we have a direct digital synthesizer feeding into a transmitter that models the RF parts of the radio, the conversion from the digital into the RF parts of the radio. And we can also model the channel in many different ways. One of the key things is how to, I may be modeling this with the system view radar model, or I may be doing it with my own IP, maybe done in MATLAB, or I'm using STK, as you see the animated picture here, where we have an aircraft flying through a scenario. Any of those can be integrated into the design. We can also add in clutter or jammers into the system, or even interference. And those can go processed through the receiver and through the radar processing, post-processing, and maybe even be fed into an instrument for post-processing or being integrating integrating physical hardware into the design.
David, that last slide didn't paint completely. Oh, there we go. Okay, very good.
Oh,
Thank you.
Oh, huh. Okay.
For me, I apologize. Go ahead.
Okay.
Sorry.
Okay, so now I'll be transferring it to my esteemed colleague, Dinqing Liu, and he will be talking about some radar models and supported systems. Thank you.
Thank you, David. Hi, everybody. Welcome to my presentation. So now I would like to introduce you the radar EW key models and supported systems. Okay. Okay, firstly, let's look at the source models. Signal source in system view design schematic page, you will see some symbol like that. We provide different signal source for you, including the list here, linear, nonlinear, coded sources, and also continue waveform, wideband, step, star source here. And also, in any time, you always can use your code. Import to system view becomes your own source. And another way to use source, you can do the combination, create a complex source. So next key model is a direct digital synthesis DDS model. When you design your phase array or MIMO radar, this model becomes very important to do the different signal generation on the baseband source side. And very important model in the radar system simulation will be the target model. So in system view, we have created a target model for you to support basic parameters such as the range, the velocity, also environment-related model. For example, the RCS type and Earth effector list here, and trajectory, and so forth. So
and Dinqing, I was going to ask you a question on that. If I wanted to integrate my own radar cross-section profile, could I do that with this?
Yes, of course. You always can use your own model coded by using either MATLAB code or C++ code and place our existing model to do the simulation. So we have this type of flexibility for you. And another important model is the clutter model. You know, in order to test your radar EW design under the complex environment, clutter always is a very important role. So in system view, we have a statistic clutter model. The probability density function include the Rayleigh, log normal, Wideband, and the K-clutter. And also, we support the clutter power spectrum density for this type of thing. Here we plot target detection under K-clutter environment by using 3D plot. As can be seen here, the clutter really affect the probability of detection rate. By the way, if you think this is not enough, you always can use your customer model. Maybe this is a recording from the field. We support such environment clutter. And another key model is the radar transmitter. In system view, we have a radar transmitter here. If you want to know the detailed structure, you can push into look the second level structure. As can be seen here, the transmitter includes the analog portion and the digital portion. For the analog portion, we allow you specify the nonlinearity, the gain, and the filtering. Also, phase noise can be specified here. For the
Ching, could I customize this and save it as my own model then?
Yes, exactly. You always can edit this model and put your design in, then save it, becomes your own model.
Thank you.
You're welcome. For the digital portion, if you push into, you will see the digital upper conversion detail structure. Okay, so you can just review it. If you satisfy, you continuously enjoy using it. If not, you can edit it, although you can delete the complete thing, put your own DUC model in. So for the RF receiver, we do the same thing. Push into the RF receiver, you will see the structure, including analog, digital portion. And you always can use this directly, or you modify it. And system view support a lot of DSP functions. On this slide, we show several DSP functions, include wave gain, pulse compression, radar detection, target tracking, and so forth. We can simply put together a test bench to test radar searching and tracking, just like this. We have more DSP library components, including moving target detection, moving target indicator, and the beamformers, and so forth. I will show you more later. Antenna model is very important in this case. Okay, so in system view, we already create an antenna model for you for tracking and searching, and you also can do the scan, moving target scenarios. And system view simulation not only consider the system level behavior model or DSP model, we also allow user to put in their RF models in to look at the detailed performance. For example, in system view, we put together system train include transmitter, receiver, and we allow you also specify your RF component by using RF link. Through this RF link, we allow you push into using the RF link simulation to construct your behavioral circuit model, or you can use the X parameter describe your nonlinearity in circuit level. And if you are ADS user, then we allow you use the ADS to system link. Push into it, you will see, you will include the circuit design in ADS for your RF component in the radar system. And all the detailed structure will be imported in system level. We allow you using system source, system measurement to get the detailed performance for you. Radar measurements are provided, including basic measurement, waveform, spectrum, signal-noise ratio, just like this. You can use system view measurement or enjoy using Agilent VSA software as a measurement to measure transmission signal, receive the return target signal, and target return with cluster signal. Look the detailed measurement. Also, advanced measurements are provided, so including the false alarm rate performance and the detection rate performance. Antenna pattern measurement are supported. Okay, you can plot 2D antenna pattern or 3D antenna pattern. In this way, you can monitor your phase array design to select TR module component to control the cost and get the calibration done. By the way, here we use the MATLAB function, the 3D plot. The system view allow you import MATLAB function as a model. Combine this model with system model, you will get the full performance. Okay. So now, previously we introduced the radar system models. By the way, we have a totally 70 models in system view radar library. And we also have 50 examples to design case study, for design case study. Now, let's tell the one example for the pulse Doppler system. So the challenge here is we want to detect target. The target return is very weak, and we have to detect the moving target in complex environments. So we're talking about the moving target, complex environment, and we use the pulse Doppler structure. We want to use the TRX performance measurement to tell you specific system performance, evaluate the system is good or not, okay? So here, okay, we use existing model to put it together system as your reference design. We have a source, we have a transmitter, we have a target model as mentioned, and we have an environment model here, either noise, clutter, jamming, interference. We have a receiver here, we have a signal processing include pulse compression, MTI, MTD, and the constant force arm control, and the probability of detection measurement. So when we run simulation, the results can be observed. At this point, we can measure the return target waveform like this. The delay reflected the target distance, and the amplitude also depends on the environment and the distance. And also, we plot the input waveform as can be seen here. In time domain, since the signal noise ratio is very low, signal clutter ratio is very low, the target just hidden. You have no way to extract the target in time domain. We have to go to the pulse Doppler signal processing and analysis signal return in frequency domain using signal processing extract the return target and do the detection. We got the detection performance here in any way. You can plot and find out the performance. And then you can plug in your own signal processing model in and study, measure the system performance until you satisfy performance. Environment always can be changed to get a group of curve for your reference. We also have an example to show the step frequency radar. The challenge here is we want the high resolution with low cost. So, of course, the high resolution can be from the regular pulse or step frequency pulse. This can be seen. The step frequency radar is much efficient. And we also have an example to show you SAR radar structure. The testbed allow you to test your signal processing under complex environment for higher resolution imaging. So this is the image radar system performance. We have a SAR source allow you specify your radar the return radar imaging here through environment, do the signal processing, extract the return target. In fact, we allow you put your customer radar imaging in to do the test your signal processing routine. Another very important design case is a phase array radar. Now, everybody is working on the phase array radar, okay? So, basically, in early stage, in early year, people just use a passive antenna system with a bigger transmitter and bigger receiver. The power loss and the scanning way is not as good, not the way expect. So now people move into the active antenna system. We just use baseband signal source. Instead, the big transmitter, we separated it to many thousands of little transmitter with the TR module structure. Then, in this way, we avoid the power loss, and the electronic scanning allow we get the better performance. So that's what people is doing. So for such phase array system, we encounter a lot of problems. The challenge is there, how we can solve these problems. The problems, firstly, is the TR module. You know, the COTS is very sensitive with the DAC, ADC, DDS. So we have to carefully make the trade-off analysis and control the cost. The system can help you to do this. We have an example to show you later. And the TR module calibration becomes very difficult because so many TR modules there. The random parameters will affect the whole performance. Sometimes they're out of control. Some adaptive algorithm can be introduced in SysML to do this thing. And also field test and how we can arrange a subarray and get the proper bin shape we expect, and how we can reduce the developing time. System will provide a number of ways to solve this problem. We will show you later, okay? So essentially, the solution proposed should be like this. Firstly, we can structure active antenna system like this. Yeah. So if you want look into the detailed performance for all the TR modules, we allow you push into in circuits level to get a detailed performance. For antenna array, we also allow you to use some EM simulation result. Then for the whole system performance monitoring, we have antenna pattern measurement, allow you to take a look how the bin and the side groups going. Is satisfied or not, then we can select right parameter to do this. Environment are available here. Not only that, we allow user to link this simulation data to Agilent hardware to generate the test data for multi-channel testing for the antenna array system, and they received from the antenna signal can be used Agilent instrument multi-channel digitizer, put it back, link it back to system to do further signal analysis to find out the RX performance. And the key model for this type of array antenna system is the phase array antenna measurement, antenna element. We have a TX antenna system, antenna model, and RX antenna model. We allow you specify the antenna location, then the bin direction, and so forth. So the angle phi and theta, x and y, and also the antenna unit shape. Beamformer is available in both TX and RX. So we already prepared some example for customer, okay? So firstly, we have an example to talk about, to study the calibration for the phase array system. So here is a phase array system. We have a transmitter and a receiver. So if we don't do anything, we can observe a phase error and amplitude error. We use the algorithm can detect the error and make a correction. Then you get the right antenna pattern.
Jing, could we optimize that or do statistical analysis on that?
Yeah, we can do both. You can optimize that, or you just do the performance evaluation directly. Okay.
Okay.
And also, we have another example to show you how to do the trade-off analysis. So in this example, we construct the complete phase array, digital phase array system, include transmitter, the beamformer, the TR modules, the target modules, radar channel, then receiver TR module, the receiver beamformer, and signal processing measurement. So as can be seen here, in the TR module, we have DDC, include DAC, so you can change the digits and get performance. Finally, you can find a best result with the lowest digit, but the performance can be satisfied. In this way, you can do the trade-off analysis. So, and we also have another example to show you how to do the multi-targeted detection. In this example, we set a complete phase array system. Here, we have two targets. Each target can be specify the location and the position. And in the phase array transmission side, we created two subarrays point to different areas to searching and detecting the target. Then we can measure the antenna pattern, and also we can do the detection. So we also support car radar. We use FMCW radar to allow you use the platform to study, to research your algorithm under the complex environment. And this one, not only in simulation, we also can link the simulation result with hardware setup in the high frequency range to test your DUT hardware. So now let's move on to next topic about EW models and support systems. So we want, the challenge for EW is we want design our EW system properly. And we also want to support not only EA, EP, and also ES. So the platform we provided allow you using the signal, the radar portion to create a signal to test your EW. And also the send out jamming and the deception can be tested in radar receiver to see if your EW design is okay or not, okay? So in our example, we already created a template, show you the digital radio frequency memory capability. Everybody want to use the DRFM to design your EA system. We have the complete setup. We have a radar source. We allow you create your EW system, EA system based on DRFM. Then the output of the EW signal combined with the original target return. Then you can study it to see your EW signals okay or not. The result is shown here, as can be seen. The original signal is here, right? And through the EW system, the output at the output EW and in the input of a radar receiver, the signal becomes something like that. The amplitudes change, the delays change, so the frequency shift a little bit. And the thing is, the EW output signal is correlated with the original signal. So it looks like a target return. In fact, it's a false target return. So in this way, you can use the platform, test your EW design. In our system view, we also provide ES receiver design. We allow you to do the direction of arrival estimation. And we also allow you to do the radar warning receiver. So now let's talk about the integrated solution using system simulation to do the hardware test. Okay? So this picture looks familiar. In fact, David already introduced you. This is a basic platform in system view. So not only the simulation, we can use this platform for simulation, but in the same time, we can use the same platform to do the test. Because in each point, we can use a link from simulation to hardware, generate a hardware test signal. And we can capture the observed raw waveform back to system view continuously to do the signal processing and the measurement, get the hardware test solution. So that's the point. So we can use this in two ways. Firstly, we can use the simulation, generate a group of signals, then download to hardware, test DUT, and use signal analyzer or scope, observe the waveform is the first use. Then we have a second way to use it. The captured, observed waveform can be captured back to system view using the VSA source to do simulation analysis to extract more information. For example, this is a pulse double system. In this point, in time domain, we already show you, you have no way to detect and return target. However, go through this type of signal processing, you will extract the pulse, and you can do the detection probability. So in this way, the system view platform extend the measurement capability for you. And another thing, is, okay, for EW, you want to generate a complex waveform to test your EW. So how to do it? We have a waveform sequencer composer to do this type of EW complex signal generation. For example, you want 3 emitters in your signal. You want to do the interference testing. You just, at the beginning, you just need to generate a simple waveform, 1, 2, 3. Then use the waveform composer, define how long you want to use for A, for B, for C. And you insert the zeros in between for the transmitting off time. Then use the frame, use the UI, click on execution. Then signal will be generated. So very easy. And this is a complex waveform generation using the composer. And also, for the ECM system, we create an example for you to study not only the radar receiver performance, but also we can test the EW system. So yeah, that's my presentation for a component and system. Now I pass this to David. Hi, David.
Okay, thank you, Dinching. As soon as I get control here, okay. One thing we're going to show you here, demonstrate here, is the ability of System View to integrate with other tools. And one of them I'm particularly fond of is the link with STK from AGI, which allows you to do the full 3D simulation of multiple targets and multiple signals in an environment. And we take the signal from system view, calculate the parameters based upon the physical results of the radar cross-section, the path loss, the path delay, Doppler shift, and everything at those time points, and process it then back in through system view and do the digital signal processing that Din-Ching so aptly just demonstrated. And here's a practical demonstration. We have, for example, this is a P3 detecting a couple of tanks on the ground. And we can do things such as track the performance. We can look at the clutter. We can look at the physical path characteristics, including terrain effects as it moves through the scenario and the system. And we could do multiple planes and targets and false targets and apply, again, the jamming and the interference that exists in a real system. In this particular case, we're also sweeping phase noise. And if I show you this example, what we have here is I'm processing the signal through that STK scenario, and I'm sweeping the phase noise of the LOs, the one LO common to both the receiver and the transmitter. And by the way, they could be separate, they could be combined, they could have jitter between them, or whatever you want. And what we can do then is process the signal, and in the lower right-hand corner, let me put my little marker here. Down here, what we have is across the x-axis, we have phase noise at 10 kilohertz offset. Now, I'm moving the full curve, but I'm just showing it, demonstrating or showing it at one value here as a reference. But what we see here is that for 90% detection, we need the phase noise at 10 kilohertz offset to be about below minus 103 dBc. But as we go through, depending on our system and at different points, we may be able to find where we need to set our LO specifications to do a more intelligent job of moving forward in the system. And I could sweep anything. I can sweep LO power, I could sweep jammer power, I could sweep the RF characteristics of the system in order to see what their effects. And we can do statistical analysis, we can do optimization, tuning, all these through the system to see all the, for instance, with statistical analysis, all the effects as we statistically vary each of the parameters in the system. Okay, another interesting technique here is we used our, in this case, we used our EM Pro package and generated a 3D radar cross-section of an aircraft. And then I introduced that 3D radar cross-section data, I introduced that into STK and took that and integrated it in at each of the phi and theta values. And then as we go through the scenario, as the aircraft goes through its logistics, you can actually see the effects as it moves through the simulation and see how as the aspect ratio to the aircraft changes, how it affects the probability of detection. Okay, well, our video isn't going to play. That's very interesting. Okay, well, there's supposed to be a video there of an aircraft going through a scenario, and we can't see that. We're going to have to work on that. But what this shows is the aircraft, and it goes through some tactical maneuvering. And as it goes through the maneuvering, we see as the aspect ratio changes, there's certain time segments. Across the x-axis is time, and the y-axis is probability of detection. And we can see as it moves through time here, at a certain aspect ratio, we lose detection over this certain area. So if you're trying to avoid being detected, this would be a good way to do it. Or if you're trying to, but if you're trying to detect something, where might you lose that lock on the system? Okay, so in summary, we've talked about radar systems, and we've talked about how we can model the ideal systems and how we can model this and set it up can be created for testing from the very beginning. And for EW systems, how to generate systems, or how to generate signals, and how those can be integrated together. We can also incorporate jamming, deception, interference, and we can even do, for example, interference between comms and radar systems together. So how does one affect the other? Co-site interference, we call it. We can do model-based environments and allow us to reduce the cost by minimizing the post-processing. It allows simulations by both the RF people and the DSP people on a common platform. It allows you to incorporate your own IP. A lot of you have very large quantities of information that you can integrate in, and you have a lot of people who've been doing this many years who have a lot of knowledge, and by integrating that in, that'll be available for years to come. And of course, we can integrate with the virtual scenarios and allow us to do processing in real tactical situations. And I'll pass it back to Carmina.
Great. Thanks so much, David. Thanks, Ding-Ching. In a moment, we'll begin today's question and answer session. Also on the line, I have Darren McLaren, who's our product planning manager for SystemView. You can also ask questions for him. Please remember to fill out the survey that will automatically launch at the end of the webcast. As I mentioned at the beginning, by submitting this survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. So please take a moment to do that at the end of the webcast. Now on to the question and answer portion of the event. As I mentioned, we'll try to answer everyone's questions live, but if we run out of time, we'll respond to the remaining questions via email. Okay, so here's the first question, Ding-Ching. How do I set up a phased array radar system in simulation to detect multiple targets?
Yes, yeah, we can do it using the existing model library. First, you can use a template on the example radar DAR. There's a multi-target detection example. Start from there, you can see we specify 2 targets in the design, and each target can be specified the position, the speed, and the distance. And in the transmitter, we specified 2 sub-array structure to point to different area to do the searching and the detection model. So you can extend a little bit of this from, for example, you want 4 target, you just copy-paste this type of thing, and you specify different parameter, let the target in different position. And the transmitter side, you can copy-paste it to do the full sub-array system to the point at different region. Finally, you finish your multi-target detection. Thank you.
Okay, thank you. Here's another question from Francis. For Ding-Ching, can we design a multi-static radar system using SystemView? Yes,
we can do it. Yeah. Right now, although we don't have exactly multi-static radar example here, but all components is there. We just need to put together. For example, you can create a transmitter using existing radar transmitter plus the antenna model, then point the beam to some direction. Then you can planning your receiver in different locations using the receiver model and with the antenna model, then you can start to do your simple two-static, bistatic radar search. Then you can increase the number of receivers to do the full multi-static radar research. Okay, thank you. Good question.
Okay, great, thanks. Here's a question for David. This is from Alan. We're trying to apply digital predistortion to our radar waveform to suppress some out-of-band signals without having to rebuild the system from scratch. Can SystemView do this?
Sure. It sounds like, a very interesting application. We've done a number of application notes and web presentations using SystemView together with ADS to perform digital predistortion on commercial wireless systems. We'd be interested if you would like to contact either your local ESOF salesperson or somebody on this web, as Carmina will show you in a few minutes here. We can get back to you on that. Thank you.
Sure, and here's a question maybe for Darren. This is from John. I'm testing my algorithm with SystemView. In which format can I enter my existing algorithm in SystemView? Can you export it into an FPGA?
Thanks, Carmina. The algorithms, SystemView is a multi-language modeling system. So we can bring in MATLAB code and C++, VHDL, et cetera, and GUI models. So there's a variety of standard modeling interfaces. I think by and large, a lot of radar engineers are using MATLAB models, and M-code is directly usable and debuggable in our platform. As far as code generation of VHDL or Verilog, we have a general purpose design flow that goes through a fixed point library and is able to instantiate VHDL hardware. And so from that perspective, there's a general platform capability to be able to do that. It's not necessarily radar specific.
Hey, thanks, Darren. Good to hear your voice. So here's a question for Dean Ching, and this is from Matthew. One signal's nice, but I want a waveform with approximately 20 different emitters to test my EA system. What's the best way to create that?
Yeah, thank you for the very good question. Essentially, if you want to create a complex waveforms such as 20 different emitters using regular tool, it's very difficult. So, however, we just created a waveform composer for our customers. Using the tool, the UI becomes very easy to be used. We give you a table. You can specify the 20 different emitters line by line. And each line corresponding to a very simple waveform. Then use the tool. You just try to run it at the beginning simulation. You verify the waveform, you satisfy, you just need to hit the button, run. Then the simulation data can automatically transmit to the hardware to do the EA waveform testing. Thank you.
Very good. David, here's a question for you. And this comes from Kurt. I need to model how my radar system might interfere with the commercial LTE networks in a foreign country. Can your software do this?
Yes, in fact, we've been asked to do that already, but it's very interesting. SystemView has a complete set of both radar library, but we have a complete set of standard compliant LTE libraries too. And so we can evaluate the performance of an LTE system and induce the signals from a radar on top of that and see at what level do we degrade the performance of the system so it becomes unacceptable. Thank you.
Thanks, David. And Darren, here's one last question. Let's see, this is from Frank. We use MATLAB pretty extensively already. Does SystemView solve any particular class of problem than Simulink?
Thanks, Carmina. As a modeling tool, we're already fairly compatible with MATLAB, so it's not like it's an either or at that level. And as far as Simulink, we don't really comment on other people's capability, but what I would say is just, to emphasize some of the strengths that you heard today. There's one was a strength of RF modeling that we link to our own RF system planning tool, as well as to direct COSIM with ADS and Golden Gate and other real RF tools. You saw a number of links to wideband test equipment that is and features that integrate the simulation environment with sort of the real world. And then the ability to have these, you saw my colleague Ding Ching showed a number of pre-built sort of examples that are already built for you. So there's dozens of these examples that are usable as templates that save a lot of time. They're like reference designs, and since radars are a one of a kind, there's really not a standard radar. What people often use SystemView for in this space is to model other people's radars that they're either trying to do countermeasures on, or modeling things that they aren't working on themselves. So they take their own models and surround it with commercial models for other pieces, and create very quickly these scenarios that to either test simulation algorithms or download the test. So I think that the ability to go anywhere in the design process and do baseband and RF together and link all these domains together is a fairly useful thing. And then there was a link to third-party applications like EM and terrain modeling and stuff. I think the ability to link to a number of these other domains is a useful system-level cockpit, if you will.
Great. Thanks so much, Darren. And it looks like that's all of the questions that we have time for today. We will follow up the rest of the questions by email, but before we close, David, any closing comments to our audience?
Well, I'd like to thank everybody for attending, and we're always interested in learning more and seeing more applications of the software. So if you have any questions, please contact your local sales applications engineer or somebody from the web here, or myself.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.